All right, everybody, hello and welcome back. Today what we're going to do is we are going to work on graphing logarithms. So the most important thing that we want to remember is logs and exponentials are inverses. The reason that's important is because we are going to start by graphing the inverse of every log, which is an exponential, because that's something we're a little bit more comfortable with, and then we are going to work on flipping our values to get the actual graph of the log. All right, so for our first example here, we have f of x is equal to log base 2 of x. Now, it's a little bit difficult for us to envision how to graph logs. It's a little bit difficult for us to figure out some good x values to plug in here, or we can fill out our table. So instead what we're going to do is we're going to use the idea that we know logs and exponentials are inverses. So the inverse of this function would be 2 to the x power. Now that's something we're a little bit more comfortable graphing. So if I wanted to, I could create a short little table over here with my two values being 0 and 1 that we want to plug in. Now 2 to the 0 power is 1 and 2 to the first power is 2. So if we wanted to graph this, we'd be graphing the exponential 2 to the x power. However, we got to keep in mind that we are graphing the inverse, the opposite. If you think back to our day of notes where we were finding inverse functions, what we did is we would switch the x and the y. So it's actually how we're going to graph logs today. All we have to do is take the inverse function and then flip our x and our y values in each point. So instead of 0, 1, we're going to have the points 1, 0. Instead of 1, 2, we're going to have 2, 1. So now if I go ahead and plot those values, we have 1, 0, 2, 1. It looks a little bit strange here, right? Because we're used to having our exponentials curve up or curve down, depending on how it is, where we basically use our x-axis as our basement, as our bottom floor. Now, we got to keep in mind that exponentials and logs are inverses, so it's going to be a little bit different. Instead of having our exponentials come closer and closer to our asymptote, to our asymptote, but also our x value, our x-axis, instead, they're going to get closer and closer to our y-axis because they're opposites. So the graph is actually going to look like this. So if you were to tilt it on its side, it would look like an exponential, but this is actually a log. And now we would think back to how exponential functions have a horizontal asymptote at y equals 0. That means the opposite of that means instead of having a horizontal asymptote, we are going to have a vertical asymptote for all logs. This vertical asymptote before any transformations is going to start at x equals 0. So this is our log function. Again, if you were to tilt it on its side, it would look like an exponential. Now we can come back and we can fill out the rest of our values. Now increasing and decreasing is something that gives us a little bit of trouble. All it is asking us is, hey, for what x values are we going up? For what x values are we going down? Well, if we notice, we read a graph from left to right, so we are going up the entire time. That means for our entire domain, we are going to be increasing. Now I'll come back to this because we're going to fill out our domain first. If you take a look at the graph, sorry, I was a little bit too far, you can see that we go all the way to the right towards positive infinity. And then we don't get to the negative side of our x values. Instead, we get stopped by that vertical asymptote at 0. So that is actually going to be our entire domain from 0 to infinity. Now that means we are increasing for the entire domain, which is 0 to infinity. If we look at our range values, we could see that we should be going all the way down in one direction and then up in the other. So that means there is no limit on our range values, and our range is going to be negative infinity to infinity. Typically, you might realize that, hey, this kind of looks like what our domain and range look like for our exponentials, except they're actually flipped. And the reason that is because, again, we are working with the inverse. So in this case, for all log functions, the range is always going to be from negative infinity to infinity. Now we can do our end behavior, and if we think about all that means is what's happening on the right side as x moves to infinity. The function f of x is doing what? And then as x goes to the left, our function is doing what? Now just looking at that picture here, we could see on our right side when x goes towards infinity, our function is going up. We're going up and to the side, so that means our function, where are we, is going to be going up towards infinity. Now on the left side, we want to get towards negative infinity, but we don't actually ever get there. We get stopped at that y-axis. So this actually isn't going to be infinity, negative infinity, because we never get to that side. Instead, the furthest we go is 0. As we start getting closer and closer to 0, our function is going down towards negative infinity. Now what you might notice is we have our domain, and then we have our range. Again, that's very similar to what we had for our exponential functions. So this is essentially all we have to do when we are graphing exponentials. When we are graphing logs. We start with our inverse exponential, we flip in the x and the y value, and we get our table here. Now, if we wanted to, we could apply our transformations, but this one doesn't have any, so let's take a look at our next example. In this example, we have g of x equals log base 3 of x minus 1 plus 2. Now, it's important to remember that the parent function of this is going to be without any transformations. That means log base 3 of x. Again, it's a little bit difficult for us to graph logs, so we're actually going to start with the inverse, which would be 3 to the x power. So we can create a mini table where we have nice x values to plug in. We get 3 to the 0 power, which is 1, and 3 to the first power, which is 3. So 0, 1, 1, 3 are points of our inverse function, 3 to the x power. Because logs and exponentials are inverses, we're going to flip them before we put them into our table. So we're actually going to have 1, 0, and 3, 1. Now, this one's a little bit different than the last one because we actually have some transformations we need to take a look at. Just like with our previous functions, the rules are going to stay the same. So when I am adding or subtracting at the end of my function, this is going to be a vertical shift. In this case, it is up 2. And then I have some addition and subtraction directly attached to my x value. And what that means is we have a horizontal shift. Although it says minus 1, remember horizontal transformations are a little bit weird and they're actually the opposite. So instead of going left 1 towards our negative values, we're actually going to go right 1. All we have to do is apply these to our table. So I'm going to take my x values and I'm going to add 1 to each of them. And then I'm going to take my y values and add 2. So my new table for g of x is going to be 2, 2, and then 4, 3. Thinking back to our last problem, log functions have a vertical asymptote that starts at 0. Well, if you think about it, everything is shifted to the right 1. It doesn't matter if we're shifting a line, a vertical line up or down. That doesn't change anything because it's always continuous in both directions. But that horizontal shift right is going to be important because it not only shifts our points, but it will also shift our asymptote from 0 to 1. So our vertical asymptote is going to be at x equals 1. Now let's plot our points. We've got 2, 2, and then we have 4, 3, which should tell us that our log function, I could draw a little bit better of a line here, it's going to look something like this. Again, if you were to tilt it on its side, it would look like an exponential, and that's because they're inverses. So now to answer our remaining questions, we could really just look at our graph. If we take a look at increasing and decreasing, again, read it from left to right. We're going up, so that means we will be increasing. And we're increasing the entire time, so it's going to be for our entire domain. So let's figure out what our domain is going to be. Now looking at that graph, the furthest to the left we go is this asymptote. So that's going to be 1. And then the furthest to the right, well, we've got an arrow pointing up and to the right, so that means positive infinity. Finally, the range for all logs is the same, but again, just look at the picture. We're going down on my left side and up on my right, so my range is going to be negative infinity to infinity. That tells us that we are increasing for the entire domain, which is 1 to infinity, and now we can do our end behavior. As x goes to the right, our function g of x is going up. So we're going up towards positive infinity. As we move to the left, the furthest left we can go is 1. And as we do that, our function starts to hug that asymptote as we move down. So that means we're going to be approaching negative infinity. So this is what goes into graphing logs. It's really one extra step from graphing exponentials. We have to come up with the inverse function table and then flip our x and our y values because exponentials and logs are inverses. Now, the last thing I want to quickly touch on is you might end up having to graph the natural log of something. And now what that really means is, I should have an x in here. What that means is, again, we want to take away our transformations, and we're looking at the parent function, the natural log of x. In order to graph logs, we use the exponential inverse, which in this case would be e to the x power. So that's the table we're going to want to start with. We still have our nice x values. We'll plug in. And then we just need to flip these for the table. So we will end up with 1, 0, and then e, 1. Now, it's important for us to remember that e is approximately 2.72, so we're just going to use that approximation when we apply our transformations. Luckily for us, these transformations, the only one we have is a vertical shift up 2. So those values actually aren't going to change. I still have e by itself. Now, let's just say for argument purposes, we had the natural log of x minus 2 plus 2. That means we would be adding 2 to each of these numbers. Again, I don't really expect you to have a perfect value for each of these. This should be 3, 2. And then we'll have e plus 2 and then 3. If you just plug this into your calculator, you get approximately 4.72, which we would just have to estimate as our x value in that point. Okay? So graphing the natural log really isn't any different. It's a little bit strange because we end up dealing with e, but again, e is just an irrational number that we work with sometimes, kind of like pi. All right, as always, thank you for listening. If you have any questions or concerns, please feel free to reach out.